guys, and welcome back. We're having a fantastic show. I think you're all learning lots because I am too. We've got a question from Bryce, which we're going to get to straight away. Are you ready for it, Phil?
Absolutely.
Okay, fantastic. Here it is. Okay, is it a dipole if the electronegative are different and asymmetrical?
Okay, absolutely. Good question. There's a couple of words there which are quite difficult and people need explained. Okay,
yes,
so Bryce
please.
says, is a molecule a dipole? First of all, let's just explain what the word dipole means. A dipole is a molecule with a clear plus side and a minus side. That means that if I draw out my molecule, that means that all the pluses bunched on the one side, all the minuses bunched on the other side. So I'm going to take a look at a molecule which explains exactly what Bryce is talking about. If something is a dipole, I will find that there is a plus on the one side and a minus on the other side. Let's take a look at an example. I know, for instance, that HCl is a dipole. The question is, how do you at home know that HCl is a dipole? Well, I've got to take a look at the electronegativity numbers on my periodic table. You will get these during an exam, but just for reference sake, I'm going to write them on the board and then you're going to follow at home. The electronegativity of hydrogen, if you're watching in Tracy's show, this should be very, very obvious. The electronegativity of hydrogen is 2.1. That's a value which comes directly off your table. Chlorine has got an electronegativity of 3. That means that it has a desire for electrons of 3. Now that just means that hydrogen and chlorine, because they're both nonmetals, I'm going to identify the bond between them as covalent. However, the sharing between them is not even. I can see that chlorine really likes electrons, hydrogen not quite as much. I'll find that 2.1 and 3 are a certain distance apart. I call this the electronegativity difference. So what I'm going to say is that that is called the END, the electronegativity difference, is equal to. I just take one and subtract the other and I see what it is. If I take 3.0 and I subtract from it 2.1, I get a value of 0.9. Now this number seems quite meaningless. What does it actually mean if they have an electronegativity difference of 0.9? That means that the chlorine is going to grab all of the electrons, all of the negative to its side, and hydrogen is going to be left slightly without. Now this has got a very important effect. This means that chlorine is going to grab some of those electrons in the sharing agreement between them, and this is going to be a polar covalent bond. Now I just want to make sure that people know that there is molecular polarity and bond polarity. They are related, but they are not the same thing. All I can decide from these two numbers is that covalent bond going to be polar? And the answer is yes. Okay? So I know that chlorine itself is going to make this nice negative cloud around it. So this means that chlorine is going to be negative. It's going to have all this extra negative bits on it. And what's going to be left behind is hydrogen, and hydrogen is going to have a little bit of positive on its side. So I leave behind positive on the one side and negative on the other side. That is a very good dipole. I've got plus on the one side and minus on the other. Sometimes they just draw it as a blob and there's minus on the one side and plus on the other side. Now Bryce said, if the electronegativity is different, and it is, the 3 is different from the 2.1. That means that I've got minus and plus separated from each other. This means that one wants the electrons more than the other one. So if I've got a molecule which separates out the plus and the minus, I have what's known as a dipole. So this word is very, very important. A dipole means that I've got a plus and a minus. He mentioned another word, asymmetrical. Now asymmetrical means unbalanced. It means that if I chop the molecule in half, it has got different pieces. Let's see. I've first decided that I've got a molecule which is polar in terms of bonds, but we're going to try to see if those pluses and minuses don't cancel out. So if I chop my molecule in half, I hope that you can see that we don't have two equal halves. I've got a plus on one side and a minus on the other side, and that's the second requirement for making a polar molecule. I'm just going to go back for a second, and I just want to remind people, so I've got to check first for a polar bond, and is the molecule symmetrical? Well, in this case, let's take a look and let's answer these questions. So I said, is there a polar bond? And the way that you do that is you compare the electronegativities. If they're very different, that means that you have a polar bond. So in this case, I know that my END, or my electronegativity difference, was 0.9. That means that yes, there is a polar bond. Okay? What about the question, is the molecule asymmetrical, meaning unbalanced? Well, definitely, yes. I've got a hydrogen on one side, which is positive, and I've got a chlorine on the other side, which is negative. It is definitely asymmetrical. So if I answer yes to both of these questions, this means that I've now figured out that my bond is going to be polar, and if the molecule is unbalanced, that means that I've got a molecular polarity going on. I need a polar bond, I need it to be asymmetrical, and if the answer of both of these is yes, that means that my whole molecule is a dipole. That means that I've got a polar molecule. I hope that answers Bryce's question.
I'm sure it does. Are you ready to answer two more short little questions? One
Absolutely.
from Mutenda.
Okay.
Okay, now actually let's do Takalani's first, because Takalani says, does dipole only happen on hydrogen?
Oh, okay, right.
Something maybe.
Can I only get a dipole on hydrogen?
Yeah.
Okay.
I think that's what he means. Takalani, hopefully.
Absolutely. Very good question, Takalani. Now, Takalani's asked the question, does a dipole only happen when there is hydrogen? Absolute answer is no. I can get dipoles between other types of atoms as well. I'm going to show you one where I've got a dipole, but I've got a molecule which is going to have a dipole inside it, and we're going to try to see if that's bonded together with dipole-dipole bonding. Okay, so let's just make a little bit of space underneath here, and let's try to see if I can't explain what Takalani is talking about. So he's saying, can I get a plus separated from a minus without hydrogen? And absolutely, I can start to talk about polar bonds. I'm going to draw out carbon monoxide. We're going to deal with carbon dioxide a little bit later, and we're going to talk about that particular dipole. Well, if I draw out carbon monoxide, you'll notice something very, very strange. Carbon monoxide has got carbon with some unpaired electrons, and we'll deal with that in another lesson if need be. But let's just discuss the relationship between carbon and oxygen. Carbon has got a very low electronegativity. If you look on your table, it's 2.5. Oxygen is very hungry for electrons. It's got a very high electronegativity, a very high electron affinity, another word that you should be familiar with. And that means that it's got a value of 3.5 versus 2.5. If you find the difference between these two, I find that there's an END or an electronegativity difference of 1.0. That's very, very large. Now, some of the viewers at home might say, okay, well, what is big? If you've got an electronegativity difference larger than 0.4, that means that you have a polar bond. So what I'm going to do is I'm just going to say that the carbon and the oxygen don't have an equal sharing agreement. I've got a slightly positive carbon because it's left without some electrons, and a slightly negative oxygen. Okay, so I've answered yes to the first question of my two-question test for polarity. I've definitely got a polar covalent bond between carbon and oxygen. It's not an even sharing. Is the molecule symmetrical? Well, if I draw a dotted line through the middle of the bond where they're bonded, I can see that there's a plus on one side and a minus on the other side. That means that they are asymmetrical. So the word up at the top of your screen there means that they are unbalanced. This guy is a dipole. I can see a plus on one side and a minus on the other side. I hope that answers Takalani's question.
I'm sure it does. Okay, and here's a very quick one from Shepard.
Sure.
How best can we define dipole-dipole if asked in an exam?
Oh, very good question.
Yeah.
Okay. Dipole-dipole is a type of bonding which occurs between two polar molecules. One polar molecule is attracted to another polar molecule because plus attracts minus. Let me actually draw that out so that you can explain it. Let me just say that again. Dipole-dipole occurs between two polar molecules. So I'm going to draw that out for you. What happens if I've got another polar molecule? So there's one carbon monoxide. I'm going to draw another one and we're going to see how they line up. And then I'm going to show you how we explain them during an exam. If you had another carbon monoxide molecule, how would you line up another carbon monoxide? Remember that all of these are plus attracted to minus. So if I line up another one, it's quite easy to see that the carbons positive would be attracted to the minus of the oxygen. Now, dipole-dipole, attraction between two polar molecules with plus on the dipole. Remember that this is a dipole, and I can call it a dipole now because I know that it's a polar molecule. One dipole is attracted to another dipole because of electrostatic attraction. There it is. I have my electrostatic attraction between the minus on the oxygen on one molecule and the positive carbon on the other. I hope that answers that question.
That's fantastic. Okay, I'm going to ask you for another question because Eden has asked me a question, and then somebody else asked me as well. It was Sintemba, also asked the exact same question, so I'm guessing that a whole bunch of mindsets are wondering this. I think it's a bit off, but what is the difference between intermolecular forces and intramolecular forces?
Okay, very, very tricky, especially if English is not your home language. There's one vowel which is different, inter. Okay, I'm going to explain exactly what's going on there because I've talked about both types of forces today.
Yeah.
I've talked about intra and inter. Now, the difference between the two of those, I'm just going to write this out because there is a small difference between there. Intra and inter. Now, the question is, what is the difference between intramolecular and intermolecular? Now, intra means within or inside. And the difference between them is right at the end there. Intra means that we are inside the molecule. That means within. Inter means between. So it means outside the molecule. Now, if you think about this, one of the examples that I used to remember, inter is quite a commonly used prefix for something. So international means that we are talking about things which are outside our nation. International means between two nations. If it was intranational, we'd talk about inside. Now, I hope that answers that type of question. Now, let me just give you a few examples of what an intra and an intermolecular force is. Intramolecular, we're talking about covalent, is a very good example of intra. Once we've got covalent, we can start talking about intermolecular forces. These guys, intermolecular forces, would be your hydrogen bonding, they would be your dipole, and your London forces.
That's actually another one. I don't actually remember who asked the question because you know when you get these comments, they just carry on going. Guys, I'm trying to ask as many of your questions as possible. Would you be able to go over the London, what did you call it?
The London forces,
yes,
absolutely.
Because I think a few of you are wondering, like you've never heard of this, of the London forces before. Okay. So that would be fantastic if we have time.
We can make time. Okay, London forces are actually quite difficult to grasp because they're not something which is normal. Because if I start thinking about, okay, well, what if there's a polar bond but the thing turns out to be absolutely symmetrical? What if your molecule is not polar? I know what to do with polar molecules. They just line up, plus, subtract, minus, and I have dipole. But in the case of something which is non-polar, I'm going to have to be dealing with London forces. Now, the way that you can describe when London forces take place is that London forces are forces of attraction between two non-polar molecules. Now, a lot of viewers might be saying, okay, well, if I've got something which is non-polar and non-polar, how do you get the two to stick together? And I mean, this is actually quite a difficult concept. How do you get one ping pong ball to stick to another ping pong ball? You can put them together with your hands, you can lie them next to each other, but at the end of the day, they're going to fall apart very easily. And when substances are bound by London forces or temporary dipole forces, that's the other name for them, we find that it's very, very weak. Now, the explanation for them is actually a little bit more complex. Now, intra and intermolecular, let's just make a little bit of space, and I'm going to draw you a molecule which is non-polar and see how that might stick to itself.
Well,
okay.
Khomotso is also asking, I just wanted to say her name and, chat about, she says, how do molecules become non-polar whereas they contain polar bonds? That's kind of what we're talking
very,
about,
very good.
Right?
Absolutely, because I'm about to draw a molecule which does exactly that.
So there you go, Khomotso, it's coming up.
Okay, Khomotso, you seem to be on the ball. We talked about carbon.
She knows.
Absolutely. If I have carbon monoxide, I can see that there's a clear plus side and a minus side. Now, most of you have never seen a structure of carbon monoxide because carbon usually bonds to oxygen to form carbon dioxide, the stuff that you're breathing out at the moment, or at least I hope you are. So if I draw my structure of carbon dioxide, I actually want you to draw it ahead of me, and I want you to see if I can answer those two questions about polarity. If I draw carbon, and if I draw a structure for carbon dioxide, I will find that I've got one double bond to oxygen, and I've got another double bond to the other oxygen. First question I ask myself, is there a polar bond? Well, we decided earlier, because the difference between oxygen and carbon was larger than 0.4, that meant that yes, there was a polar bond. Okay? Because I knew that there was 2.5 over there as an electronegativity, and 3.5. That meant that the electrons were being pulled towards the oxygen. What about on the other side? If I have a 3.5 pulling on the other side, I've got a tug of war going on here. If oxygen is pulling from this side and I've got an oxygen pulling from the other side, I've got something very interesting happening. I've got an electron which is being pulled in both directions. So if the electrons are being pulled towards this oxygen and pulled towards that oxygen, I've got a bit of a problem. Now I'm going to answer those two questions. Is there a polar bond? And the answer to this one is yes. However, when I look to see if the molecule is unbalanced, I run into a problem here. So what I'm going to do is I'm going to chop my molecule in two, and we're going to see. I hope that you can see that both sides of the molecule are exactly the same. I've got electrons being pulled towards this oxygen, electrons being pulled towards that oxygen. I have polar bonds, but the molecule is symmetrical. That means that I'm nicely balanced either way. That means that this guy is going to be nonpolar. Now, to answer the other question, how do I bond this to itself? I now have decided that I have a nonpolar molecule. How do I stick this onto another carbon dioxide? Well, all that I'm going to do is let's just take that line out of the way and let's try to see if I can't bond another carbon dioxide to this. Now, that's very, very difficult to understand. Why would one carbon dioxide stick to another one? Well, the question is, where does the plus-minus attraction come from? If carbon dioxide wants to stick to other carbon dioxide, it's going to be very different. And we can't rely on this plus-minus attraction because there is no reliable plus and minus. But one of the really strange things is I want you to imagine what is surrounding these atoms. I start to picture each atom being clouded by electrons. Each atom has got its own personal weather system of electrons. So I'm just going to draw a nice big cloud for all the atoms inside there. All of these are going to be negative. You've always got this nice big cloud of electrons floating around our two molecules. Now, where London forces or temporary dipoles happen is because these shift around just the way the clouds do around the world. At any one point in time, there might be clouds in Johannesburg, but not in Pretoria. Might be in Cape Town, but not in Durban. That means that electrons can temporarily move around. If my electrons find themselves more on the right-hand side, what we'll find is that we'll find a negative region over here. This is temporary, and that's where the name temporary dipole comes from. If I've got some of the electrons bunching up on the one side, what it leaves behind is a slight positivity on the other side. This is called a temporary dipole. I've temporarily made a plus and minus because this is completely random and doesn't happen very often. However, this allows the molecule next to it to become influenced. If I have negatives on one side of the molecule touching the nearest molecule, it's going to chase electrons away. Now, you don't need to know this, but that process of chasing these electrons around is called induction. You might remember it from grade 11. Okay? So if I've got electrons which are being chased away, that leaves behind a very attractive positive side. And what's going to happen is that this temporary positive and that temporary negative will attract each other. But this force of attraction is very, very weak, and that's why the carbon dioxide that you breathe out is a gas. These molecules don't stick very well to each other. You can buy solid carbon dioxide, proof that you can get carbon dioxide to stick to other carbon dioxide. That solid carbon dioxide is actually called dry ice. The next time you buy ice cream out of those big boxes at soccer or a rugby or a cricket game, what's happening over there is that somebody is selling ice cream which is being cooled down by the evaporation of solid carbon dioxide. I hope that answers that question.
I'm sure. We've got so many amazing questions. I can't believe, I think we've got like 15 minutes left.
Okay.
Can you believe it? I can't believe it. But anyway, let's go to a break, and when we get back, we're going to try and get through some more of your questions. Guys, don't leave those seats. In grade 12s, don't forget that you guys are on next. See you after the break.